Okay, let's carry on with 2025 May June paper 42. We have completed 6 questions. Let's go to the 7th one. This paper is more challenging now. Okay, we have completed this part. I give you 2 graphs. There's a potential difference across here as 12 volt. And there's a resistor, there's a capacitor, then you close the switch. You close the switch, the charge on the capacitor against the potential difference across the capacitor is given by this graph. Then the current flowing through the circuit and the potential difference across VR is given. Then you are asked the relationship between VC and VR. Right? We have established VC equals VR. Then you are asked to calculate capacitance. Right? Go to definition, then take a point on the graph. Right? Easier to read from here, 12 volt, and then read from here. Sorry, 12 volt, and then read the chart from here. Right? Any point can do. Calculate out. Resistance R can get this AS work out reading the graph only. This is an easy question. 12 volt divided by the current VR 8.0 kilo ohm. Any comments so far?
No.
Need me to explain further? Let me know. Time constant is R0. P will calculate, R will calculate, and time constant is RC. Change to SI unit, calculate out 4.8 seconds. Use figure 7.3, 7.2, 7.3, 7.2, 7.3, and the answer in A to explain why variation of Q with T is exponential. Right, this one is same as we have done in the previous question about radioactivity. Right? Charge is directly proportional to current. This is the alternative answer. How to remember? Basically, the derivation is I equals dq dt. That's why charge is proportional to current. From here, charge is proportional to current. And current is the rate of change of charge. That's the definition. Especially you got that. Then your current is V over R. Since there's a decrease, this derivation which you don't require, just to help you understand why they choose this answer or that answer. Right? Current is decreasing. Then replace your V with Q over C. So you can see that I is proportional to Q. Q is proportional to the rate of change of Q. This is just a repeat. Q is proportional to the rate of change of Q. That's important. That's the first one. That's the second one. And you get this equation. Any comment? The others I memorized without understanding. I just try to derive for you. Any comment? Memorize that. Memorize.
No.
Okay, let's go to the next question. Question 8. Figure 8.1 show the circuit that produces rectification of an alternating input voltage. That's your alternating input voltage. The input V in is sinusoidal. The rectified output V out is applied across VR. That's the output. That's the input. V in with time t as amplitude V naught and Vt. Right? That's the graph. That's the input against time. The root mean squares. The root mean square value for V in is 60 volt state. The type of rectification produced by the circuit in figure 8.1. What's the type of rectification? Yep.
Half wave. Looks like half wave.
Single diode. Doesn't matter direction of diode. Right? It's half wave rectification. Calculate V naught. This is just a simple way of letting you earn the mark lah. Memorize the formula lah. V root mean square is V naught over root 2. V naught is V root mean square root 2. Okay. Resistor R has a resistance of 45 ohm. Right? 45 ohm. Across, assume that there is no PD across the diode when it is conducting. Determine the peak power in the resistor. Right? That's your V naught. You have calculated. And peak power is V naught square over R. Okay, put in your value. R is 45. Calculate out. On figure 8.3, sketch the variation of power in resistor with T, where T equals 0 and T equals 2T. Okay. Only this part will pass through lor. Because of the direction of the diode, and then this part will pass through. This top part don't pass through. Okay. Power has no negative value, that's why it's drawn this way. Negative, square it, I square R, or V squared over R, right? Turn positive. Right? That's how they give the mark lor. And thus I got 2 hump there of width 0.5 and 2 sections of 0 of width 0.5. That's your 0. That's your 0. As long as you get that 1 mark there, all the humps drawn having a width of 0.5, minimum at P equals 0, minimum P equals 0, and peak at P equals P naught. That's P naught. Right? Just now they don't bother about the P naught. As long as you got a hump, this one they worry about the P naught. Correct sinusoidal shape with smooth trough sitting on the axis as P equals 0. Right? That's your P naught. P naught. Okay. Okay. Use your answer in B to explain why the mean power in the resistor is a quarter P naught. Mean power within each hump is half P naught from symmetry of the curve. This one is AC lah. The mean power for AC alternating power is half peak power lor.
One loop. Just one loop, right? Yeah.
not one loop. When it's sinusoidal, you square the voltage, it comes out positive. So I have shown you that it's half V naught.
Oh yeah, no.
Then this
The
another
mean
half is
power of one
taken
loop is
off.
half V naught.
Another half is taken off, so it becomes a quarter, lor. Right? Additional half factor from removal of half the power. Right? Another half cycle is gone. So half the power is gone, so it's a quarter, lor. Okay?
Mm.
Right? You got that peak power. There's an equation. Mean power is root V square over R. Right? V root mean square is mean power times R. Right? So we have say it's a quarter of this one. Quarter of peak power. R is 45. We get 4.2. Then,
Okay.
okay, next part is more challenging. This is the first time it comes out. I've been teaching it for years and then never come out. So I've more or less thrown it out. But anyway, review. Investigate how the current passing through a photocell depends on PD across the cell. There's a photocell. Usually the cathode is made of photosensitive metal lah. And then the electromagnetic radiation will fall on the cathode lah. So you have to look at the power supply in this case. In this case, what is happening? The cathode is positive. It should be negative lah. Negative so that when electromagnetic radiation fall on the cathode, electron is emitted. You have anode positive, anode will attract the electron. Right? But in this case, you are putting the cathode positive, so you are attracting the electron back. Can you understand? These are, you are stopping the electron.
Mhm.
So without any voltage, you are collecting the electron emitted. But as you increase more positive for cathode, then the current becomes smaller and smaller. Any question you want to ask?
Wait, so it gets smaller and smaller?
The cathode is usually negative because you want the anode to be positive. So the electron is attracted by the anode. But in this case, the power supply is reversed. The cathode is positive, the anode is negative. So the positive charge cathode is attracting the electron emitter is attracted back. So the most energetic one will only reach the anode. So as you increase the voltage of the positive potential on the cathode, less and less electron will reach the anode until finally at a what I call coupling potential, Vs, no electron will reach the anode at all because you are pushing the electron back. Emitted, pushing it back. So the most energetic one will be pushed back. No electron will reach the anode. So no current will flow. Can? Any question you want to ask?
No.
Okay. Right, this is positive lah. Right, so the anode is attracting the electron emitted lah. This is the normal case lah. This one hardly come out lah. Only this question came out. So this part, anode is positive. This part, anode is negative. Right? This part, anode is negative. Cathode is positive. They are basically pushing the electron back. So at Vs, the most energetic electron is stopped. That's why it's called stopping potential. at a particular voltage called the stopping potential or cutoff voltage, no current will be detected. So stopping potential is a negative voltage that must be supplied to stop all electrons from reaching the collector or the anode. Okay, cathode is positive connected. So the graph is still the same, except we call Vs, this is your frequency. Right? Except the gradient is different, the y-intercept is different. You divide by E, that's all. Function divided by E. This is still F naught. Threshold frequency. That's our equation. Same thing, we just divide this equals EV, EVS, we take the E divided by E, we get that equation, no? Right? Then compare, that's the equation of the straight line. Okay, any comment or anything not clear?
Okay.
Okay, what is meant by photoelectric effect? Can remember without looking at your answer?
Like emission of electrons.
From a metal surface,
Yeah. Emission from the surface metal when the radiation is greater than the threshold frequency.
no need for threshold frequency coming in. Emission of electron from metal surface when electromagnetic radiation is incident on the surface. Okay, when electromagnetic radiation is incident on the surface. Sorry, you know why I put it this way. Yeah, why is this one disturbing? Okay, this one you can see that there's a surface that emit the electron. There's a vacuum. And that surface is positively charged. So it means you are electron emitter, you are trying to pull it back by increasing the potential across this is the cathode, this is the anode. Okay, photoelectric effect is investigated in two stages using circuit shown in figure 9.1. The polished metal surface Y is illuminated with electromagnetic radiation of frequency F and constant power. That is your electromagnetic radiation, frequency F, constant power. In stage 1 of the investigation, the frequency is set to constant value. That's the frequency. Frequency is constant. The current I in the emitter is varied by adjusting the potential difference. That's the potential difference. You can change that. Measure the current. Figure 9.2 shows a variation of I with voltmeter reading. That's your voltmeter reading. There's a value Vs that's usually called stopping potential, but you don't need to know, not in your syllabus. But you know it's Vs, they tell you value Vs or V at which the current just falls to zero. Right? So at Vs, the current falls to zero. Okay, any comment or any query so far?
No.
So electron emitted by the surface is being attracted back. So the more potential increase, the more greater the potential difference, the less electron will flow until Vs, then no current will flow because all the most energetic electron that is emitted is attracted back. None will reach the anode or the metal plate. So in stage 2 of the investigation, stage 1 is repeated with different value of frequency. You change the frequency. Just now the frequency was constant. That's this one. As the frequency is varied, the voltmeter reading Vs, at which the current is just falls to 0, is measured. Figure 9.3 shows the variation of Vs and Vf. So to relate to you, we are looking at this part lah. Right? Except we call it negative, we call it positive lah. And then we are also looking at this one lah, where we change the frequency lah, and then we measure Vs lah. That's this graph lah. Explain with reference to photon why Vs depends on frequency of the incident electromagnetic radiation. Yep, you want to try?
Let me see what I wrote.
Say again.
Yeah.
Any comment or anything you want to say? Basically, Vs measure your maximum kinetic energy of the emitted electron. That's why Vs depends on your frequency. Greater frequency, greater energy of the electromagnetic radiation. Right? That's your answer equation. Greater frequency, greater energy. So yeah, work function is constant for a particular method. Kinetic energy will increase with frequency. That's why we get this equation, this graph. Right? This one is measured by Vs. Current falls to 0 when applied voltage equals to energy per unit charge of emitted electron. Energy of photon depends on frequency. That's what it's saying here. Maximum energy of electron depends on energy of photon. Right? This one is constant. That one depends on this frequency. Can you understand the answer?
Yeah, quite. Based off the formula.
This one is just defining for you the stopping potential lah. Is energy divided by charge lah. That's the definition of potential difference lah. That's what they are saying here. Current falls to 0 when applied voltage equals energy per unit charge of emitted electron. Okay, no problem.
Yeah.
State 3 quantitative conclusion that can be drawn from the result in figure 9.2 and 9.3. Use the space for your working. Right, that one. F naught look. Just show frequency. Right, the more obvious one lah. No need to go and do complicated one. They give a lot of. It's not a fair question lah, because this one is not mentioned in the syllabus, but they are trying to push it through lah. That's why I say A2 is more challenging now lah. Right, threshold frequency. Read here. F naught. Planck constant. You can get it from here. Right, where we refer to. Right, this is Einstein's equation. Right, we replace this one with EVS and divide by E. That's why we get the equation. So we can get Planck's constant from the gradient, and then work function from the y-intercept. Right? Planck constant, you can get that. Right? Work function is just your h times f naught. Right? You can get the answer. Okay. Your current, right? Current is NE over T. You can get the number of electron emitted per second from here. Right? There's the number of electron emitted per second. Right? Where the potential is different. Potential is zero. There's the amount that's collected, the electron that's emitted as the electromagnetic radiation shine on the metal plate. Electron is emitted, so it's detected by the anode. That one you didn't disturb it at all, no potential different. That's all the electron that is emitted. Any comment? Don't go into all that. These are all complicated stuff. Go to the.
Yeah, it's everything complicated.
That's why I say it's not, in a sense, it's not fair, but that's what it's the first time I see it. Go to the obvious one, no? Right? Threshold frequency, Planck's constant, treat that as EKS, EK max, and then as your frequency, then you can calculate your work function, Work function, as long as you can get your threshold frequency, then times your Planck's constant, you get that. Any comment or anything you need me to explain further? I
Oh,
calculate for you some of the other stuff here. Yep. Any comment on it?
no.
Not clear? Okay,
Okay, okay.
radioactive decay is a spontaneous process. State the meaning in context of the term spontaneous. Okay, can remember? You got 10 more minutes.
Spontaneous.
Yep. Spontaneous is what?
Not affected by the external factor environment.
Okay. Decay is not affected by external or environmental factors. Two radioisotopes, X and Y, each decay to form a stable isotope. A sample of initially contained only atoms of X, that one, atoms of X. At a time, at this time, the activity is for A. That's your starting activity for X. Another sample initially contained only Y, right? Activity A. Figure 10.1 shows a variation with activity of each sample with time t equals 0 and 60, from 0 to 60. Right? Usually nuclear physics, you can assure one question will come out. Photoelectricity, not every time. Sometimes will come out. Okay. So complete table 10.1 to give the expression in terms of either or both A and T for the quantity indicated in the sample. Right? That is your formula that we are going to use. Half-life. Half-life, you just, right? For A to 2A, that one. So it's 2T. Then this A, half-life to half A. This 3T. Right? That's 2T. Or this one, 2T. And then use this equation. Divide by half-life, you get that. That's 4A. Then you use this equation. Right? You want N is A over lambda. Lo. A in this case is 4A. Lo. 4A. Then lambda. That's a lambda. Okay. Substitute inside here. That's why you get your 8AT ln 2. Lo. And this is 3T. Half-life. Decay constant. Ln 2 over 3T. Lo. Right? Using this equation. Is A. Right? Replace it. N is A over lambda. Lo. A over lambda. A, in this case, this is your lambda. Lo. Can? Any comment? Anything I
Okay.
need? Okay. That's the marking scheme. Lah. Determine in terms of T, the time at which the two samples will have equal activities. Right? It is given in your formula sheet. You want the activity to be the same. Okay. You
Okay.
got that? 12T. Can or not? Can or not? Can or not? A will cancel off. Then you just take exponential. Ln it. Ln it, it becomes that one there. And ln 4. Ln 4. And this one becomes just that. When you take a ln of it, A and A will cancel off. Then you just take this across. Take this one across. Okay.
Mm.
Radiation detector is placed near to one of the sample. Explain why the count rate measured by the detector is less than the activity of the sample. Can? Can or not?
Less than the activity of the sample, because
Basic idea is
like the activity is in the radiation is all directions.
the particles is emitted in all
And
directions.
some radiation might not get absorbed.
So you are only active. The radioactive substance emit radiation in all directions. You are detecting in one direction only. The other one correct lah, is absorbed by the right radiation emitted in all directions, not just in one direction of the detector. Some radiation is absorbed by air, correct? Okay, these are other acceptable answer lah. Okay, let's go to the next one. Okay, we go to variant 44. right? We go to 2025, May, June, we are in 44. Right? Anytime it will cut off. So I see you next Wednesday. Continue to do this paper if you haven't completed it, and then go to May and March of 2005. No? Define gravitational field. Usually that is the answer. But now the examiner put it as the answer is this one, force per unit mass. The marking scheme that most of us are using are most of the time reliable lah. But I've observed that for previous years, there are some mistake there lah. Somebody may have taken the advantage to change it lah. So the most reliable is from your lecturer lor, who download it from Cambridge website lor. Now I have no access with it.
Okay.
So I'm not teaching. So I'm just downloading it from outside source. Okay, so I don't know. Unless they have changed the definition to this one. So the only way is to check with your lecturer, provided your lecturer doesn't use Cambridge download from Cambridge rather than use outside source. Okay, that is the usual definition. Region of space where test charge experience a force. Unless they ask you for gravitational field strength, then that's the force per unit mass. But that is the marking scheme for outside source. Okay, that one you have to check with your lecturer. Gravitational field strength G at a distance x from the center of the uniform spherical planet of mass m is given by the equation. G is the gravitational constant. The distance x is greater than the radius of the planet. Describe the pattern of field lines outside the planet that represent the gravitational field due to the planet. Anytime will cut off so I guess give you the answer Any comment? Radial towards the center. That's why 1 mark here, radial. Towards the center, 1 mark. At plane Y, a small change in vertical height near the surface of the planet. G may be